So we have a pin-connected truss that is geometrically symmetric and subjected to a force of P and 3P. So here's P, here's 3P. The problem says it's geometrically symmetric, which means the truss itself is symmetric, but the truss with these forces is not symmetric. So you got to be careful. All of the forces here are not going to be the same as the other side by virtue of these forces here that break the symmetry. So part A, identify all zero force members. We know that this pin is capable of putting two force components on this joint A. So we may be tempted to say that we can't say anything about these members right here. They're not necessarily zero force members. But if you look at our truss as a whole, the only external forces on it are vertical forces, which means that this force will be a zero right here. Just imagine you did sum forces in the x for this entire truss as one big system. So there's really no force horizontal from the pin at A, which means this CA must be a zero force member. CA, if it's activated with force, is going to bring with it some horizontal component, and there will be nothing else to balance this horizontal component. BA can only act either up or down. So there's nothing to balance this force right here, therefore CA is a zero force member. At joint B here, CB is going to be a zero force member. DB can either go up or down. BA can either go up or down. But CB has to go either right or left, and there's nothing to balance it. Looking at joint C, the only two forces we have acting at that joint C is EC and CD. Those are the only two forces acting on this joint C. And the only way for two forces to add up and equal zero is if they're in completely opposite directions, which is definitely not the case. So both of these members here have to be zero force members. Focusing on joint E, I noticed that this P is downwards, which means to balance it we need some sort of upwards force. Well, ED is not going to fight against that. It can only put a force to the right or left. But EF is this way, which means it will have a vertical component. So that's good. Well, EF will also bring with it a horizontal component, and that can be balanced by ED. So it's possible that E is in equilibrium under the influence of all these forces and members here. So I can't say for sure that any of these are zero force members. Joint D looks fine. We can have a up, a left, a right, and a downward, so looks like equilibrium is definitely fine with all four of those at play there. Same thing with F. We have four forces in all different directions. I'm sure they could all balance each other just fine. Looking at H, I know HG will be a zero force member. And a lot of people think that, wait, how can that be a zero force member if I have this 3P going down here? Won't HG need to fight that? Well, you make a valid point, but remember, free body diagram means we only look at H only, and we don't care about anything else. So looking at just H, FH could go to the left, HJ could go to the right, that's great, there's balance. But HG, there's nothing to balance it. Therefore, for equilibrium of this pin H, it must be zero. Okay, instead of continuing this way, I'll work from here, because it's usually easier to spot working from our support reactions. At O, we know the roller can only put an upwards force, MO can either be up or down, probably down. NO will bring with it some sort of horizontal component which has nothing to balance it. MO can't, and the roller can only push up, so nothing can fight against this horizontal component here, which means NO cannot be activated. There can't be any force here because it'll bring that troublesome horizontal component, which has no partner to balance it. Looking at M here, we have another one of those T situations. This MN has nothing to balance it, so that's 0. Looking at N, we only have two forces acting at this joint N, and again, for two forces to act on something and bounce each other, they must be in complete opposite directions. So both of these are going to be zero force members. Same exact situation at L. 0 and 0. Looking at pin K, we have an up, or maybe a down, which means we'll need another up or down. All right, here's another up or down, so that's fine. This GK here is a horizontal, and it has nothing else to balance it, so it must be 0. GK. Looking at J, JK is going to be maybe an up. We'll need a down to fight against that. Well, that down can be provided by the downwards component of JG. Well, if JG is going that way, it's going to bring with it a left, which means we need a right to fight against that. And HJ can be that right. So everything's balanced there. I can't say that anything is 0 from the perspective of J. H is the same. We have a left or two horizontals battling each other, so that's good. Looking at G, we have this downwards right here, so we'll need an upwards. Well, the upwards may be provided by GJ. Well, GJ brings with it a rightwards, and that rightwards can be balanced by either DG or FG. So it looks like all those forces could possibly be in equilibrium. I can't say that anything is 0. So there are all my zero force members right there. Okay, so part B, determine the force P if member JG experiences an axial force of 20 kips in tension. So, I have a choice. Should I do a free body diagram on G or J? Well, if we did it at G, we'll have one force unknown, FG, 2, DG, and 3, P. Whenever we're doing analysis of a point, we only have two equations, some forces in the x and some forces in the y. We can't do sum of the moments because a point is not an extended object. We need an extended object with dimensions and lengths to calculate moments. So only two equations, which means I can only handle two unknowns at most. I have 3 at G, so I'm not going to dive into G. My only other choice is J. Looking at J, we'll have one unknown and two unknowns because GJ is known. So analyzing J would be good. So here's my free body diagram at joint J. GJ is in tension. And just as a reminder, let's go through how I know for sure that GJ is in tension. Why do I draw it like this rather than the other way? Well, if I do a quick FBD on GJ, tension means that we are stretching it like this. And of course we know it to be stretched with a force of 20 kips. So it's a Newton's third law argument here. What's putting this force on this member, GJ? Well, it's really the thing that's over here. It's joint J. So if joint J is putting this force on GJ, then we have to flip that statement. GJ is putting the same force, 20, but in the opposite direction onto joint J. So that's how I know that this is in tension. Long story short, if the force is away from the joint, it's in tension. If it's towards the joint, it's in compression. So I'm also assuming that these guys are in tension, and that's usually a convention that we're just told to assume. So I can write my some force x and some forces y equations, but first I need some sort of angle for this 20 right here. Well, looking at my main picture, that angle can be found by analyzing this right triangle. Right triangle, the opposite is 10. The adjacent is this 4. So the tangent of that angle will equal the opposite 10 over the adjacent 4. And I'll get 68.2. So I have HJ going to the left, so negative. And I have the x component of that 20 also going to the left. So I'll get a negative 18.57 for HJ. All these forces will be in kips. I can do my sum forces in the y. And there I can do 20 cosine, that's 68.2, to grab that negative y component. And of course JK is acting downwards. And I'll get a negative 7.43. So both are negative, which means both are acting in compression. Now what I'm tempted to do is, now that I know that, I want to flip my directions here on my picture. But here's what I'm going to do. For the rest of this problem, for all the other joints we're going to analyze, like for instance joint H, even though I know HJ is in compression, I'm still going to assume that everything is in tension. And I'll just plug in a negative value. I'll just plug in this whole negative value in for HJ just to reflect that it's in compression. So for the remaining joints, I assume everything to be in tension, even though I might already know it to actually be in compression, and I'll just plug in the numbers, even if those numbers are negative, meaning it's actually in compression. I think this is the way that most professors want you to do it. So I'm not going to go back to G because nothing's changed. I mean, we already knew JG. The only new things we figured out was HJ and JK, and they're not in contact with G. So I'm just going to move on to H, and then F, and then E, and that's how I'll get P. Or if I wanted to from F, I could go directly to G and figure it out from the 3P. So different ways of doing it. So looking at joint G, only two things acting on it, which really means that FH must equal HJ. And of course, if HJ is this, that means FH must be the same thing as well, and also in compression. Looking at point F, though, I have a problem. This is one unknown, the second unknown, and our third unknown here. 3 unknowns here. We can't do anything. And that really stinks because that breaks my whole plan, what I thought I was going to do. So, kind of retrace my steps. I started here, I can't go this way, I can't go this way. The only other way is to go down. And I start thinking how that's going to play out. Well, I can go down super easily because there's not much craziness going on at these two joints. It's only vertical members. So we'll end up down here and we'll basically figure out this roller force. Well, thinking about that roller force makes me think about a free body diagram on the entire system. Doing that usually allows me to get both of my support reactions. If I quickly imagine a free body diagram on the entire system, I'll only have two unknowns. One of them will be AY here, and the other will be P. Because remember, this OY will be unknown at this point. So doing a free body diagram on the entire thing, I can use two equations, some forces Y and some moments, to figure out AY and P. So I think that plan will work. So doing an FBD at K, I only have JK and KM. So they both have to be the same. JK is negative 7.43 in compression, so must KM. Doing a quick FBD at M, same situation. These two must be the exact same. So KM and MO are the same as JK, negative 7.43 in compression. Looking at our joint O, I know that this roller here can only push up. This roller really only provides a surface with which to push up on something. So there's really no hard thinking required there. O must push upwards on joint O with a strength of 7.43. Yeah, I don't really put tension or compression here because this is a support reaction, not a member. It can't really be in tension or compression. So now doing a free body diagram on the entire system, I know my external forces on this entire thing is only going to be this 7.43, this unknown AY, and my two forces P and 3P. So, summing my moments about A leaves only my unknown P. So that should be good. So the moment of my P here, its moment arm will be this distance from E to D. And that distance is going to be the 6. Remember, our truss is symmetrical. The dimensions on the right match the dimensions on the left. So we have P acting with 6, and this P wants to spin us counterclockwise about A, therefore it's a positive moment. Our force 3P, its moment arm will be the distance from D to G, and that will be this 10 right here. And 3P wants to spin the object, or this truss, clockwise about A, so it's going to be a negative moment, 3P times 10. And my 7.43, its moment arm is this full distance right here. That's going to be 2 of these 10s, so 20. And it wants to spin the truss this way, so another positive moment. So I'm getting P is a positive 6.2 kips. Positive means that this P force is actually acting downwards. So part C, if P is 15, determine the axial force in member FG using method of sections. So FG is right here. So I will want to make my section cut through here, and I'll want to choose my left-hand side as my section to analyze, because this is a smaller thing. I definitely have less going on. Either side, though, should allow you to get the answer. So let me quickly scan this section and figure out how many unknowns I have. I'll have FH, perfectly horizontal, that's one unknown. FG, another unknown. DG is a third unknown. Luckily P is known, that's going to be 15. But I also have a force here, AY. That's 4 unknowns. That's not good, but I remember I can do a free body diagram on my whole system to determine AY as well as OY. Got to remember that the 7.43 over here doesn't apply anymore. It was based on information from part B. So let me do a quick analysis on our entire system. We have 3P. P is 15, so this is going to be 45. P here is 15. We have AY, and this is going to be OY. So really only 2 unknowns here, AY, OY, and AY is really the one I want. So how about I do some of the moments about O to figure it out. So AY's moment arm is going to be that full 20. Wants to spin us clockwise about O. Negative moment. The 15's moment arm here will be a 10, a 10, and a 6 here to make a 26. Wants to spin us counterclockwise about O, so a positive moment. And the 45's moment arm will simply be this 10 here, and it wants to also spin us counterclockwise, so a positive moment. If we run that calculation, we'll get a positive 42 kips for AY. So now I'll bring back in my section, and now we know this. So really, I'm tempted to do some moments about a point, because that's how, we usually do, start some moments and then some forces x, y. But I realize that FG has a negative y component. We know both of the other y forces. So some forces in the y should allow us to solve for FG directly. Of course, I'll need to know some angle for FG. Well, looking at my main picture, we know it's symmetric, and I know we have this 68.2 over here, so I know that this must also be that 68.2 because of symmetry. So on our picture, that 68.2 will be this one. So I have a 15 downwards, a 42 up, and I can use the cosine of that 68.2 to grab the downwards y component of our FG. And I'll get a positive 72.7 kips in tension. And again, because I drew FG directed away from the joint here, that means it's assumed to be in tension. Long story short. Now for part D, using our results from part C, determine the axial force in member EF. So EF being right here. And we need to figure this out using method of joints. Well, how to approach this? Well, I might go directly for it. Can we just do an FBD on joint E and figure stuff out? EF will be one unknown, ED will be two unknowns, but that's it. Nothing else is touching this joint E. EC is a zero force member, and therefore is not really happening. So I can just do an FBD on joint E, and my answers will come out. So to do my equations here, of course I'm going to need to know some angle, looking up at my main problem picture. Here's this purple right triangle, and here's the angle that I want. Well, the opposite of this angle will be 4. The adjacent here will be this, which will be 6. And doing that inverse tangent, I'll get a 33.7. So I can grab EF just by doing a sum forces in the Y. Got a 15 downwards, and EF sine of 33.7 upwards. And we'll get a positive 27 kips for EF. And of course, since we're getting positive, that means EF is in tension. And that does it for this problem. So I hope everything made sense. Feel free to ask me any questions you may have in the comments.